Covers Module 7, Part 6, which is about imaginary and complex numbers. This is the last section of Module 7 before we move on to Module 8, which is our final module of the semester. So please make sure you're completing your guided notes as you follow along. So previously, I had told you that we could not take the square root of negative numbers, right? If I took the square root of negative 16, I told you that does not exist. And that's true that it's not a real number, but it does exist as an imaginary number, which is what this video is going to cover. So we have our imaginary unit I, and I is the square root of negative 1. So if I was to square I, that would be the square root of negative 1 squared, which would be negative 1, because squares undo square roots. So for any real number b, if I put a negative in front of it under a square root and a square root only, because I can take cube roots, right? I can take fifth roots of negative numbers. We pull out this square root of negative 1, we pull out this I. And you always have to pull out the I first. So I could think of the square root of negative 100 as the square root of I times the square root of 100, because by our multiplication property, I can pull this out. So the square root of negative 1 times the square root of 100. This would become I times 10, which is 10I. So we pull this apart, we pull out the negative, we take the square root of our positive number that we have left. The square root of negative 1 becomes an I, and we simplify our square root. So our order in which we're going to represent things is we're going to have like our real number first, our constant, followed by an I, and then followed by the radical. And we treat I kind of like we treat variables, but we need to remember that I stands for the square root of negative 1. So if I have negative square root of negative 36, that negativity hangs out on the outside. I could rewrite this as the square root of negative 1 times the square root of 36, which would be negative I, square root of 36 is 6, so I'd have negative 6I. For problem 3, I'm taking the square root of negative 2. I could rewrite this if I wanted to as the square root of negative 1 times the square root of 2. Square root of negative 1 is I, and I can't simplify the square root of 2. So I would just have I root 2, and that's totally valid. For problem 4, I'm going to pull this apart. So I've got the square root of negative 1 times the square root of 54. And 54, I know I can simplify. It's got a perfect square hiding in there. It is 9 times 6. So I'm going to have I 3 root 6, because that's how the square root of 54 would simplify. You can think of it as the square root of 9 times 6, which would be 3 square root of 6. So my final answer would be 3I root 6. When we're working with them, we have to remember that we need to pull out the I first, the imaginary part first. That's really critical. Otherwise, we're going to get a different answer. So the square root of negative 4, that becomes I root 4, so just 2I. The square root of negative 9 becomes I root 9, which would be 3I. If I multiply these together, I get 6I squared. Remember, I squared is negative 1. So here I have the square root of negative 4 times the square root of negative 9. I'm going to pull out that I first. So I'd have I root 4 times I root 9. This would be 2I times 3I, which gives me 6I squared. And we have to remember that I squared equals negative 1. So this is going to be 6 times negative 1, which is negative 6. And if I'd gone ahead and not pulled out the I first, I would get the wrong answer, because this would become the square root of 36, which would just be 6, and that's not correct. Don't do that, okay? Next, I've got I root 3 times I root 7. that becomes I squared root 21. So negative root 21, because that I squared is a negative 1. Let's switch to a nicer color. How about blue? If I've got the square root of 2 times the square root of negative 8, that's going to become I root 2 times I root 8. That'd give me I squared root 16, because 2 times 8 is 16. So I have 4 times I squared. 4 times negative 1 is negative 4. Lastly, on problem 4, I only have one square root of a negative variable here, of a negative number here. I've got I root 5 times the square root of 6. That leaves me with I root 30, and I can't simplify the square root of 30 any further because there's no perfect squares hiding in there. When we're dividing complex radicals, we have to keep in mind that we need to rationalize our denominator. Remember, we don't like radicals in our denominators. And even though I doesn't exactly look like a radical, we have to remember it's the square root of negative 1. So we don't want that in our denominator. Here I have the square root of negative 75 over the square root of negative 3. I'm going to pull out my i's first. So I've got I root 75 over I root 3. The square root of 75 simplifies into 5 root 3. So I have 5 I root 3 over I root 3. And then those I root 3's are both going to cancel. So my final answer is just going to be 5. That looks a whole lot nicer than what we had before. In problem 2, I've got the square root of negative 32 over the square root of 8. That's going to give me I root 32 over I root 8. And I need to simplify these roots. I know the square root of 8 is 2 root 2, so I'd have 2I root 2. The square root of 32 is 16 times 2, so that would give me 4I root 2, and again, my I root 2's are going to cancel. So I'm left with 4 over 2, which is just 2. So we do have to make sure we get rid of all radicals in our denominator. Let me come up with one more little simple example. So if I have 2 over I is the square root of negative 1, as I said. We don't want that in our denominator. So I'm going to have to multiply it by I over I, which would give me 2I over I squared, which becomes 2I over negative 1, which would just give us negative 2I, because we don't want any radicals or i's in our denominator. So complex numbers are numbers that are made up of a real part and an imaginary part. So we've got imaginary numbers, we've got real numbers, and complex numbers are both of those together. So an example of a complex number could be 2 plus 3i, it could be 4 minus I, it could be negative 7 plus 10i. These are all examples of complex numbers because they have a real part and an imaginary part. When I'm adding and subtracting complex numbers, I can only add the real parts and the complex parts. Again, this is another example where we treat I like a variable. So if I have 2 plus 3i plus 6 plus 4i, I can add my 2 and my 8 because those are my real parts. And I can add 3i and 4i because those are my complex parts. All of our same rules apply. So in example 2 here, I'm going to have to make sure I distribute this negative. So I have 6 plus 5i minus 3 minus 2i. Combining like terms would give me 3 plus 3i. And there's no need to factor a 3 out of this. We're really just practicing adding and subtracting complex numbers. We don't need to factor at this time. For problem 3, I have 4 plus 3 plus a negative 6. 4 plus 3 is 7, minus 6 is 1. 2i minus I becomes 1i, plus 3i is 4i. So my final answer would be 1 plus 4i. When we're multiplying and dividing complex numbers, we have to make sure we're distributing, we're foiling. All of those same rules still apply, but we got to remember this one extra piece of information that I squared is -1. So let's practice multiplying some complex numbers. If I have 4i times 2 plus 3i, that's going to become 8i plus 12i squared. And then we substitute in. We remember that I squared is -1. So I've got 8i plus 12 times -1. That becomes 8i plus 12, sorry, not plus, minus 12i, or plus a -12i. And one thing we really want to remember is that we always want to have our real part before our imaginary part. So I would rewrite this as -12 plus 8i. For problem 2, we are going to have to FOIL. So I've got 12 minus 6i plus 20i minus 10i squared. That gives me 12 plus 14i. -10 times a -1 gives me a +10. 22 plus 14i. Let's try that again. 2 times 1 is 2, minus 10i plus 3i minus 15i squared. That gives me 2 minus 7i plus 15, because I squared is -1. Final answer would be 17 minus 7i. And again, when it comes to multiplying and dividing complex numbers, no radicals in our denominators. So I need to multiply by the conjugate. So I've got 5 minus 2i over 5 minus 2i. That gives me 40 minus 16i plus 45i minus 18i squared over 25 minus 10i plus 10i minus 4i squared. So in my denominator, I'm going to have 25 plus 4. In my numerator, I've got 40, -16, and 45. That gives me 29. So plus 29i. And then for -18 times I squared, that becomes a +18. So I have 58 plus 29i over 29. And then we have to see that we can simplify. 59 divided by 29 is 2. 29i divided by 29 is I. For problem 5, I just need to multiply by an I over I to get rid of that radical in our denominator. I've got I plus I squared over I squared. So I have I minus 1 over -1. That gives me -I plus 1, which I'm going to rewrite as 1 minus I, because again, we want that real part first. For 6, this is another example where I need to multiply by the conjugate. The conjugate of 5 minus I is 5 plus I. I'm going to have 10 plus 2i minus 15i minus 3i squared, all over 25 plus 5i minus 5i minus I squared. So I've got 10 minus 13i plus 3 over 25 plus 1. That gives me 13 minus 3i over minus 13i over 26. And I can pull out a factor of 13. That gives me 1 minus I over 2 is my fully simplified answer. The last thing I want to show you is an interesting property of I, and there's a group that we study in higher level math courses called the quaternions, that are made up of pieces of I. And the reason is this: if I've got I and then I multiply I by another I to get I squared. So I've got I I multiply by I get I squared. Well, I squared is -1. And then if I multiply that by another I to get I cubed is going to be I times -1, so -I. And then if I multiply that again to get I to the 4th, that's going to be I squared times I squared, based on our exponent rules, which would be -1 times -1, which just means it's 1. That's very convenient. And if I multiply that by I again for like I to the 5th, I would get back to just I all by itself. And if I just keep multiplying by I, my answer is always going to be one of these 4 options. I, -1, -I, or +1. Side our drawing of this little closed circle that we call the quaternions. Let's work through some examples. And I'm going to do I to the 10th first. So I could think of this as going around my circle, taking 10 steps. So here's step 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my 10th step puts me back at -1. So I to the 10th is -1. And you might be like, oh my gosh, Dr. Miller, how am I supposed to do something like I to the 24th? Well, we can think of I to the 10th as I to the 4th times I to the 4th times I squared. Well, I to the 4th is 1, and I to the 4th is 1, and I squared is -1. That's why my answer is -1. So I would always look for, can I pull out factors of I to the 4th? Because that's -1 and that's easy to work with. So I think of 17, if I've got I to the 17th, 16 is the biggest multiple of 4 that goes into 17. So I could write this as I to the 16th times I. Well, I to the 16th we can write as I to the 4th times 4 times I. So I've got 1 to the 4th times I. That's just going to give me I. When I've got I to some negative exponents like I to the -2 and I to the -1. So if I have I all by itself, that's I to the 1st, right? This right here, this point is I to the 1st. Well, that would mean if I've got I to the 0, it's 1, because any number to the 0 power is just 1. So that puts me here, I to the 0. So then I can start going backwards. This would be I to the -1. This would be I to the -2. So I to the -2 is a -1, and I to the -1st is a -I. And I could also have solved this by taking 1 over I and multiplying by I on the top and the bottom. That gives me I over -1, which is -I, but I didn't want to do that. Next, I can think about I to the 43rd. I'm going to rewrite that as I to the 40th times I cubed, because 40 is the biggest multiple of 4 in 43. So that's like I to the 4th to the 10th times I cubed, which is 1 to the 10th times I cubed, which just gives me I cubed, which is -I. Lastly, I to the 24. Well, I to the 24, 24 is 6 times 4. So I've got I to the 4th times 6. Well, I to the 4th is 1. 1 to the 6th is just going to be 1. So that's how you work with the I all by itself. The tip is to look for the biggest power of 4, the largest multiple of 4 that'll fit into the exponent that you are working with.